So, maybe what the muscles we focus on is not cardiac, not smooth, we focus on skeletal. That's the biggest muscle that we focus. Cardiac, a little bit we get to the heart, but we really don't focus it as much as this type. Now, a muscle fiber is equivalent to a muscle cell. Another name for a muscle cell is a what? Myocyte. So a myocyte is the same thing as a muscle cell or a muscle fiber. All three terms are interchangeable. And what we're going to do, we're going to actually build the muscle now by using this stuff here to create it, okay? So we're going to see that a fascicle, like a popsicle, is at least 10 or more have to be bundled to create this, okay? So then we have to wrap all this stuff together to keep it in place. So we have endomysium, perimysium, epimysium. What you're going to see, the epimysium totally wraps the whole muscle. Once you see that layer, you have an actual muscle, like a biceps, a brachialis, whatever. Now you have an actual muscle. Endomysium is going to wrap these guys. So it's kind of like taking shoestring licorice and you separate them all out and you get saran wrap. And you wrap each individual piece of licorice. That would be endomysium. Now you get at least 10. You need a minimum of 10. 10 up to 100. That's how many sit in a fascicle. So you're going to get at least 10 of these. Put them together, and then you're going to bundle it. You're going to wrap it one more time. So you get 10 individually wrapped licorice. Now you wrap it one more time. And what that wrapping would be is perimysium. Now you take all these fascicles, so say if you got 10 bundles, and you wrap it one more time with epimysium, you've created a muscle. And when I told you how you can get this point across, we would do a food lab. So in other words, in lab that day, we would build a muscle from the licorice. And if they didn't act like animals and smack one another and everything else, then I would say, okay, you can eat the licorice if you eat the lab. That would be your reward for behavior. And that's all you're going to do with teenage boys. Like, woo, anything you reward them with, they're happier than anything else in the world. So they wouldn't be beating one another up and everything. Now, see this picture here? This one looks like you're getting a test. That's one of your pictures. You're going to have 4 pages of pictures worth 20 points. It's 100 questions altogether. 20 points and 1 pictures. 80 points was your our famous true or false. Word bank. Word bank, you have multiple choice. Right? You do have a word bank. And people still do bad. So it shows you that word bank doesn't mean anything. You know, it's like Dr. Goff says, in Wanda Goff. Stuff those students, yeah, you have a word bank, it's in here. You have everything in the world in there when you walk into a desk. It makes you famous. If it is, brain's working, you're fine. The brain's not working, even with a word bank, doesn't make a difference. Okay? Because I know campuses without word banks and they still do the same. Outcomes the same. So, I don't know. So now let's get into, so now let's build this muscle. This thing sticking out is one muscle cell. So we told you it's cylindrical, it's round, it's striatal, there it is. Multinucleated, there's your nucleuses there and there. So there you go. That's a muscle fiber, a muscle cell, a myocyte. Then we wrap it. And we wrap it with endomysium. And what this thing here is a fascicle. Which means we have at least 10 or more muscle cells wrapped in a perimysium. Then we get a bunch of them, put them all together, and wrap one more time with epimysium, and we've created a muscle. So it looks like a ham bone. You look at your hand, that's it. Doesn't look delicious? There you go. So usually when you look at a piece of steak, a cross-section of a piece of steak, when you go to eat it, you're seeing individual muscles with epimysium. It's not just one muscle, it's a bunch of them. You cut through the thigh, you cut through wherever the cut's made on the animal. Well, you can see that. And when you cook it, you break down the epimysium because this is a connective tissue. Now the key point to notice is, as we go on, the pink color fades away, but the white stays and hooks into the bone. Well, what that is the muscle tissue eventually will end, but all the myceliums continue on. And that's what creates the tendon. So your 3 layers of myceliums will create the tendons. Will create, so the 3 mycelium layers, which there's many of, will continue on beyond the muscle tissue and create the tendon, and that's what will hook into the bone. And how do we hook tendon to bone? What? Careful. Everybody agree with that? Carefully. Well, what's another? Well, it's carefully hooked here, but what holds it in place with the bone? The osteum, that's why it's mentioned here again in your handout. I don't know what the osteum has to do with muscle. Well, that will twine around the tendon and anchor it, and they kind of grow together and anchor it right into the bone. So the periosteum plays an important role to keep your tendon attached and hooked to the bone. So it grows right around it. So they kind of intertwine with one another, they're both connective tissue. And what type of connective tissue would this, that mycelium and tendon material be made of? Connective? Yeah, what type of connective?
Regular?
Who?
Dense regular?
I can't hear you.
Dense regular?
That's regular, yes, that's regular connective tissue. And where's mine? If you're late, the rule is you can bring them back.
Are you ready about it?
That's the rule. I didn't make it. I just followed the rules, I didn't know it. Okay, so you understand that now. So all we did so far was mention a few terms. 3 myceliums, endo, peri, epi, fascicle, and muscle fiber. That's all we've done. And we've just explained how we created this muscle. We did that with bone, we've done it with muscle. And that's kind of like the last organ we do that with. We don't do it with nerves.
So the peri is around the endo? The peri is around? Is the second layer around?
The peri is around, not the endo, it's around where you bundle the endos together. Okay? So, when you go home, I don't care what you use for an example. Take like 10 things and lay it out and wrap up the 10 things individually. Well, use 10 pencils, use 10 pencils. Get about 20 pencils, and then wrap 10 each individually. Then take 10, put them together, wrap them one more time, now you've created a fascicle. Then put the 2 together and wrap it one more time, you've made a tiny muscle. Okay, so that's an example of how to build it.
Can that be an assignment? I love art projects.
It's not hard. We did that when I taught at Henry, but we did it with shoestring licorice. They built their own muscles, and that was their lab, and then if they behaved, they could eat the licorice, because you know how teenage boys are, 15-year-old boys, they smack at one another and everything in their lab. So it's like, if you behave, your reward is you get to eat the licorice. It cost me a fortune. I mean, people look at me like nuts when I was buying all this licorice that night. Stop and shop and get rid of it. Because nobody really had it. So I had to buy whole licorice and then peel it and create individual muscle fibers. Are you kidding me? This is showing you here kind of how it really look. This is a microscopic blow-up of it, okay? But you can see there's a lot of fat inlaid in there, too. That's not just connective tissue. Well, just that type of connective tissue. You also have adipose in there. So lean muscle wouldn't have much adipose as comparison to muscle that's not lean. So, you know, and the fat is what? The modeling in the meat to give it its weight. Comparison to eating game meat versus eating meat grown on a farm, it's a whole different world. And they don't, you know, want the thing to run around too much, because then it gets too much to it and the meat gets tough. Not that the muscle just gets hard, even the connective tissue becomes more lean against the muscle. So it makes it a lot harder. It's not tender. You know, like veal versus there's a big blow up on that picture here. Then we go into like origin and insertion. We'll review that again. So origin is the what? Direct attachment point insertion. Indirect, what do we mean by that? It's all gibberish words which mean nothing if you don't understand what that guy's saying. It's like, okay, that's cool. But what does it mean?
Where it starts, where it ends.
And what do you mean?
Where the
Don't take that as an answer.
where the tendon of the muscle anchors and where the tendon of the muscle is attached. Finally.
Yes. So what's another way of saying that? So the origin would be its proximal attachment.
That's exactly what
And the insertion is distant. And usually the insertion is pulled towards the origin.
That's, yeah.
Oh, I was just wondering, you got it right.
Good job.
I got it right, thank you. Okay, and what is this showing you here? What are we doing to this angle?
Flex.
All right, so we're decreasing the angle, which means flexion. Okay, so that's what I mean, yes, flexion is correct, if you understand why it's flexion, that's the point. So if that angle was increasing, that would be extension. And we'll go through all movements and stuff, that would be more like on Friday. Okay, so we're all experts with this. Now let's go a little further down. And why does it look like this? You may ask. Why is it striated? Well, we're going to learn the striations are created by a thing called the sarcomere. The sarcomere is what creates the striations. Okay, so this is, the sarcomere is the functional contractile unit of the muscle. The functional contractile unit of the muscle is known as this thing, a sarcomere. Beautiful picture, isn't it?
One more time, functional what?
Contractile.
Unit of the muscle. Okay, so think about it. You have millions of these units. So they constantly just build on one another. And in physiology, we're going to learn a fancy word called recruitment. And when you hear the term recruitment, what do you think of?
Army, Marine.
All right, so how do they
Service.
recruit? All right, so what do they do then? How, when you recruit, what's that mean? I'm trying to take all of you with me, correct? So we're building up an army. We're building up a muscle contraction. So it's each one individually contracts and holds itself to the next one next to it and so forth. So it recruits, and you're going to get the staircase effect when you do muscle contraction. You do your EMGs and phys lab. And then you're going to plateau, because you're in full contraction, and eventually you're going to technique, and then you blow the muscle and go into fatigue. So those are your phases of muscle contraction. And you're going to learn what takes place and why this happens and how it happens. And we'll describe a little bit of this today to you, so you have some understanding, because you'll spend like over a week on muscle contraction physiology, not 10 minutes like we are. Yes, so you're going to go, and you're going to have a graph that you'll follow a graph, and at the same time you'll watch what's happening to the sarcomere as the graph changes itself. So these are all the fun things you're going to learn. To plot X and Y. Yes.
So you know how you have to like tear muscle to build muscle? Is this the level of organization?
Well, when you tear muscle, you don't build new muscle tissue. Muscle tissue hypertrophies. There's a difference. It doesn't do hyperplasia. It hypertrophies itself. It increases cell size.
Okay.
That's what it does, okay? So it really doesn't tear, like per se tear.
Okay.
It swells itself and hypertrophies itself. So there's a difference between hyperplasia versus hypertrophy. Hypertrophy is cell size increase, which you want.
Okay.
Hyperplasia is increase in cell number for no known reason. That's precancerous.
Oh.
Okay, so there's a difference, okay? So there is a slight difference there. If you damage muscle, will it grow new tissue? Yes. But usually if you're building muscle to get bigger, it's, instead of being this diameter, the whole muscle cell itself will increase surface area size, bigger. You know, that surface area ratio stuff that you'll learn in physiology too. So you get into that, phys. But that's more phys than anatomy. But the key here is you have to understand what happens here. So we have two type proteins that are known as contractile proteins. There's really three, but two is what we get into in anatomy, known as actin and myosin. So myosin is the fat one, or the thick one. Actin is the thin one. And how do you remember that? Well, if you stay active, you stay thin. So actin is the thin one. Okay, so it's one way to remember. So actin is the thin one, and myosin is the thick one. And the myosin has heads. Myosin heads. And what do the heads do? Well, they're gonna grab on to the actin and pull it in. And when they do, the whole sarcomere unit contracts, or pulls in, shrinks. That's what you want. Okay? So actin, myosin, and two contractile proteins. Sarcomere is the function contractile unit. Now you see this other term in your weekly notes, for those who look at that. It says sliding filament mechanism, or sliding filament theory. Well, what the sliding filament theory is this. In the presence of calcium, actin and myosin will interact, causing the sarcomere to contract. So in the presence of calcium, actin and myosin will interact, causing the sarcomere to contract. Okay, so that's the definition of that. So you're like, big deal, what the hell does that mean? All right, we'll tell you in a second. Notice this other one here that we didn't mention called titin. Titin is another protein that's in there. It looks like a spring, doesn't it? Like yellow springs. What do you think that one does? That's not involved in the contraction. That's involved, after the contraction, the muscle relaxes, it puts the sarcomere back to its normal shape. So that'll pull it back to its normal shape. Okay? That's the job of titin. And that's another one we get into detail in physiology. So there are 3 proteins in there. But to cause the contraction, there are 2. And what is needed for this contraction to take place?
Energy.
Energy, which is coming from what? What is the fuel that gives energy to muscle contraction? ATP, which comes from glucose, primarily. We can get it out of fats and get it out of proteins. But primarily, we burn carbohydrates to create ATP, which is, and the easiest way to remember this stuff, what ATP is, easiest analogy I use for this, you go to Fox Foods, you win 1,500 in chips. Now, does that have a cash value? Yeah, it's worth $1,500. But you forget to cash them in, and you leave and you go to get gas at the Speedway and you're going to pay with a chip. They're going to say, no, that's not a currency that we use. So what you're doing is taking glucose and converting it into a currency that can be used by the muscle. That's all you're doing. And the currency that the muscle understands and can burn efficiently is ATP. And then ADH, ADH doesn't go in there, but those come from vitamins. Okay, so your B vitamins primarily. That's why B vitamins give energy. Flavin and nicotinoids will give energy to help power your nervous system. But here you go. But that's all it is. When you think of ATP, it's just taking it and converting it. You want what part of your class?
I almost
You heard my magical voice and I just brought you with me.
So is the ADAG located inside the MRI?
The who?
ADAG.
The ADN? The ADN? No, it's on the outside.
Outside.
All you can see is this. So if you look here at this picture, you get the Z disc. So here's the R, H zones. Okay, here's the type of molecule which sit outside. Okay, so it's showing you what's happening from here to here. All right. So the A-band is a whole region of the darkness. Does that make sense? All right. So like in these pictures here, showing you A-band. The A-band is a region making up most of that sarcomere that you know what I'm saying? So it's not just one individual thing. The C lines are what you see, which is that top, middle part of that sarcomere. If you look here. So what is happening here? Well, what kind of happens, and just listen to so you have an idea when you get into physiology. What will happen, first we're going to stimulate a nerve. And we'll get into detail of that when we do nerve. But sodium potassium pump is what fires your nerve. And what they're going to learn, nerves are all or nothing. They don't fire a little bit, they either fire all the way or they don't. And that's going to happen when you take it from resting membrane potential to threshold. Once it hits threshold, you can't stop the nerve from firing, it's going to fire. So what's going to happen, sodium starts pouring into your nerve. Going against a concentration gradient, so it's active transport, which means I need ATP for this to happen. As sodium goes in, potassium will start pouring itself out. And when it happens, the nerve will finally peak at a positive 30 kilovolt. And what happens then, the nerve is at full firing. And it makes a charge. And this charge will jump all the way down the nerve to the nodes of the vein and all this stuff, until it gets to its end point. When it finally gets to its end point, what is going to happen is this. If we look at this picture here, it makes it a lot easier to understand. When it gets to its end point, it's going to hit a neurotransmitter and fire for specific neurotransmitter. The neurotransmitter, which is the most abundant in the human body, is ACH, which is acetylcholine. Acetylcholine. We'll talk more about when we get to the nervous system. What acetylcholine is going to do is going to jump across the gap, the synaptic gap, and hit the muscle. When it hits the muscle, it's going to cause calcium to pour out of the sarcolemma, which is the sarcoplasmic reticulum, and out it comes. When it pours out, it's going to pour into the actin and myosin molecules and take inert troponin and make it active troponin. It's a protein. Troponin's going to, an enzyme. Troponin's going to come out, and what it's going to do is make those heads stand up and become sticky. They'll grab the active molecule and they'll pull it in. That's how you get full contraction. That's all in the presence of ATP. Now, what is going to happen? Well, you need ATP to break a contraction. That's why you're going to rigor mortis, because you don't have any more ATP. You're going to full rigor. So what's going to happen now, ATPase will come back in, recycle the ATP back to ATP. So the troponin will go back to its inert state and go back into storage, and the molecules will let go, and calcium will pour back into the sarcoplasmic reticulum, which is part of the sarcolemma, and stay there. Now, you get people who have low calcium levels, and low calcium, and you can just about see the tracing of it in blood, okay? So they can have low calcium. These people get a lot of cramps in their legs. They move their foot at night and they're locked up, and they're going to bang it against the floor and stuff to break the spasm. What it is, the calcium doesn't want to let go and go back into storage because you don't have enough. So usually those patients, you put them on calcium supplements, 12 to 1600 milligrams a day with magnesium, because magnesium will get across the membrane, and you get rid of their leg cramps in a matter of 7 to 10 days. And then once you got them there, you back it off a bit and see what dose they need to maintain. Usually it's about 600 to 800 milligrams a day. You don't want to keep mega dosing because it can cause kidney stone with people who can't metabolize calcium well. So that's the whole definition of how muscle contracts. That, and you'll go into detail of that in physiology. So if you've got a condition what they call rhabdomyolysis, muscle wasting, due to too much statins, due to due to acetylnephrine overdose of using of the liver, and you can't metabolize well, so you're going to damage muscle tissue. What will happen is troponin will come out in circulation. That's how they read that you're going to drop. They'll do a liver profile plus troponin. If they think you've suffered a heart attack, besides enzymes, they'll run troponin levels. Because troponin is going to be the first thing within that hour to come out. So they can see it right away. Instead of to wait 6 hours for LDH and all these other hormones to pop, other enzymes to pop out and rise over the 24-hour period to see that you suffer an acute MI. So the troponin is a faster way of seeing it. Muscle damage. Because why? It's not going back to storage, it's pouring out into circulation because the muscle is dead. It's not doing what it's supposed to do. It's muscle wasting. So that's how you can tell muscle wasting diseases. So that's one way of investigating. Okay, so it's showing you that. And it shows you a contracted, here's a contracted sarcomere versus a relaxed sarcomere. So you can see how the Z lines pull in. Boom, boom. It's not that hard to figure that out. So in the contracted phase, the sarcomere contracts itself and pulls in. As they all do it, the muscle. So recruitment is, now usually when you move a muscle, you do not get 100% muscle contraction. You don't. Okay? You really don't get that. So here's the point we're going to go into next, then, is the electrical side of it coming in. In this picture here, we see especially when a person sneezes, no, we see neuromuscular junctions in a motor unit. Well, a neuromuscular junction is nothing but where a nerve and a muscle cell meet. It's like, my name is nerve, your name's muscle. Hey, how you doing? There you go, you meet. That's all it is. And that's where the acetylcholine will jump across, that we talked about, okay? ACT. So, what are the two biggest neurotransmitters in the body? Acetylcholine and norepinephrine. Those are your two biggest. One is parasympathetic, one is sympathetic, but the muscle system always uses acetylcholine, no matter what system it finds. They're just telling you, am I hitting a nicotinamide or a muscarinic fiber to fire the system? And that's what you're going to learn in physiology. So there's a lot to learn about how this stuff works. But I'm covering a little bit with you. Not that I'm going to hold you responsible other than what I told you. When I told you to sit and listen to me, no, you're not going to get tested on that. The point is, when you walk into physiology, it will not be a foreign name to you. You've heard it. You have some understanding. So it's going to make it easier for you to grasp it. Okay? And remember, you know, the other thing is to skeletal muscle you can put in tetany. Can the body put muscle in tetany itself? And the answer to that is no. It needs something to do it, such as a bacteria will do it, you know, or tetani will do it, or muscle stim, or a chemical on you to do it. The muscle cannot put itself artificially into tetany. Now, can you put cardiac or smooth muscle in tetany? And the answer is no. You can't, because of the calcium channels. You can't do it. Okay, it won't happen. So just remember that when we get asked those quiz questions in physiology.
Or true or false questions.
Or true and false questions in physiology. I should do them there too, just like we do in anatomy, make it fun. So what is this thing, a motor unit? Well, the motor unit is the main feed coming in to power these neuromuscular junctions. The main feed coming in. So if you have like a power strip, the main wire coming to the power strip would be the motor unit. And each one of the little plugs would be the neuromuscular junction because they're going to hook to something. Do you understand? So a motor unit is just a motor nerve coming in to cover a broad area of muscle. That's right. And usually when you use, we got different type of firing fibers. That's why you got two different ones coming in. Motor where they're holding out, extended, and away from one another, tapped up. So it would help. To keep good balance, everything's going to be working down there. Believe it or not, just cut your little toe off, your whole balance changes. And we'll show you that with David. We'll cut his toe off. We'll show you. I got a lot of experience. Okay, so that's that one. So we got a unite pennant. Of course, we have to have a bipennant. Bi meaning two. So you got muscle fibers on both sides of the tendon insertion running right through the center of this muscle. And guess what this one's name is? Rectus femoris.
Keeps your femur up.
Put your femur up. It also extends your knee, right? So rectus femoris is part of your quadriceps group. That's the most commonly pulled muscle when you pull your quads. It's usually a tear right here. When the muscle fibers and the tendon insertion meets, it tears right in its midpoint. And it hurts like hell. It's common like when you play a real heavy contact sport, especially if you're a lineman, and you're pushing someone out, you're pushing heavy with your thighs, and the person just drops. What happens? The leg goes from a flex to an extension, quick, tears the muscle. And then this thing will plague you now for months to heal. You know, so, or carrying heavy, like you do in the military, climbing up the side of a mountain, and climbing through, the legs, almost your leg slips off, almost like, oh, damn, I can't move it now. There you go. You take a muscle in heavy contracted flex state and let it drop into a quick extended state on it. That's how you do it. If the fibers don't only go fast enough, they tear. That's what she likes, is muscle tears. She brings that up. She tears muscles and just stay away from it. No, I'm just teasing her. Well, I see like a lot of research stuff. They always seem to be reading, which is really good. We'll go far in the field wherever you go into, which you like doing that. So, rectus muscles in general normally have tendon insertion. And what's the one that's the six-pack? There you go, rectus abdominis. It has 3 tendons insertions within itself, hence looks like a six-pack. That's why it gets the name six-pack. The rectus abdominis. Unfortunately, it's a very hard muscle to see in most people. It's in everybody, but it's hidden. We all keep it hidden. We don't want you to see it. It's hidden. So you need it somewhere between a six-pack and a keg. Somewhere in the middle. The keg is very expensive to maintain compared to the six-pack. You gotta put a lot in there to keep it going. So the rectus muscles usually have a lot of, have tendons and insertions in themselves. The last of the pennants, so if you're 3 or more, you call them multi-pennant. And the prime example is your deltoid. Deltoid is many muscle groups coming together with tendons and insertions within themselves. Hence called a multi-pennant.
You say that again?
It's many tendons and insertions within 3 muscle groups. Hence called multi-pennant. You can see them. You're not seeing it on the back side, but each one of these muscles would have multiple tendon insertions through themselves. So your deltoid is the prime example. There's others, but we'll just hit you with the prime example. Okay, that's what we're going to go for testing. Now, we have also the difference between the multi-tendon is a convergent muscle. Now, a convergent muscle means we have this huge origin and converge into one narrow insertion. Converge into one narrow insertion. That's why it's called a convergent. The pec major is perfect because look how big. This is all origin. All that part of the muscle is origin. There's a little insertion point on the anterior lateral aspect of the humerus. And there's nothing funny. That's that lateral ridge that goes on the humerus. That's where that goes. Because you're going to learn there's a lady between 2 majors. And the latissimus dorsi will insert between the pec major and the teres major. Hence, the lady stands between 2 majors. You will watch a major. So notice it, a broad line. So what would be its origin if this was, think of your chest, this would be clavicle, all of the sternum, down to the costal cartilage and ribs. What a huge origin this thing has. Insertion point, anterolateral aspect of the humerus. Its job is to do this. Feel your muscle, pull your arm. So that, adduct the arm across your chest. That's that. What's going to initiate the movement with it? Minor. And coracobrachialis. You got to think of the muscles. Coracobrachialis. So those are going to contract to stop. The pec major can take it over now because of the way it's built. Pull it all the way in. But other muscles will help. Understand? Other muscles will help. And the last of the muscle groups I'm going to be in today is, last but not least, our circle muscles. You have orbicularis orbis, orbicularis oculi, orbicularis ani. Where would that be? That's your front. That's where your eye is down there, your third eye. But what do they do? It's kind of like designed to close off an opening. So it's almost describing a what? A sphincter. But it's a sphincter made of skeletal muscle, not smooth muscle that you're so used to studying. Because we have tons of sphincters around hollow organs, right? Stomach, bladder, uterus. You're gonna close this thing off. So this is your learned response of when you go from diapers to the toilet. So this is where you train these muscles to work, that they just don't stay open all night and everything comes out. I mean, eventually we'll go back to that phase, but you start in diapers, you end in the pens. It's true. Unless you're lucky enough to die before. Not awful, but that's what we get to look forward to as we get older. So, next class we'll start getting into muscle groups and names and where they are and stuff like that. So we have a quiz next. You got a quiz on Friday. So far, I'm going to Class is doing. Everything's good. Other than today's not on. Everything up from the last lesson. Okay, so if you look at your study guide and you're focusing that up to the skin, you'll be fine for the quiz. Okay? It's on the black one. Let's review the study guide that I have. Got him on that. So do you understand what you need to know then? What is a sarcomere? What is it? I just said it. Functional contractile into the muscle. What are the two proteins I told you to learn? Actin and myosin. Which one's the thin one? The thick one is myosin. Which one has the heads myosin, the core myosin heads? And what is the sliding filament mechanism? In the presence of calcium, actin and myosin will interact, causing the sarcomere to contract. End of story. Everything else I told you just the FYI the next semester. Okay? To give you an understanding what the heck's going on here. Then we went to neuromuscular junction, which is where a nerve and a muscle meet. And you had to make it difficult. How does it hold together? They hang on. And then we had the motor unit, which was the main wire coming in to power this. So when people use muscle stim to treat with, you like to know where the motor units are. Every muscle has a motor unit on it, a motor point. And you want to know what that is, so when you put these electrodes over it, you get maximum contraction. Now, a TENS unit, or a muscle stim unit, will create 100% contraction. It'll contract every sarcomere. When you do this move like this, no, you're not. You're probably contracting about 60%. Even when you're lifting weights, you're probably still contracting only 80%. So what they did, for years they wondered why, back in the 60s, why the Russian power lifters would outlift the Americans by a good 100 pounds in the German. And the reason was they would use Russian stim. They'd have the electrodes hooked on these people while they were working out, causing the muscle to contract 100%, giving it much more strength and power, that when the muscle would be used on the force, it would automatically do that. And it wasn't steroids, it was that. It's all natural way of building the muscle. So you don't need steroids. Steroids aren't going to do that either. Steroids are going to hypertrophy the muscle because they're going to hold more water density in the muscle tissue to make it look bigger. Doesn't necessarily make it stronger. That's what people aren't aware of. Now, the androgen steroids will go in and play with your psyche, which make you a little more nuts, because they're going to play with your sympathetic system. That's the danger. Make you more aggressive. You would rage a lot easier. It's like that kind of a hormone. Okay, so that's all that. And then this is just looking at it microscopically, the same thing. Neuromuscular junction, muscle fiber, and the motor unit coming in. When we do nerve wonder weeks, there'll be models out showing you that. You know, the models you looked at, because you're going to do the same thing, the cardiac muscle, skeletal muscle, smooth muscle. They all need to be fired. But this doesn't have intrinsic abilities to contract itself. It totally depends on an external force to do it. With cardiac and smooth can intrinsically control themselves. There's difference. But the other thing is, now we're going to go into this next. This, what's that tell you? FOSOFG.
Those are the different types of
Muscle fibers that respond to different types of using oxygen and not using oxygen. So if you're a FG, what's an FG? Not the back word. Something no. Fast glycolytic fiber versus slow oxidative, fast oxidative. So what does that mean to you? Nothing. So, all right, who's heard of glycolysis? Versus cellular respiration.
cellular respiration is much more efficient since aerobic, it requires oxygen. So
Glycolysis is anaerobic, it don't require oxygen. And that's more like fermentation, making wine, making reds. So that's used all the time in these formations. So our muscles can run under that too, if they have to. So skeletal muscle can function without oxygen if it has to. Is it efficient? No, but it can function. Cardiac and smooth cannot. They don't have any of these fibers in them. None.
What's it fast what?
Actually, fast run. Fast glycolytic. And what does glycolysis mean? The breakdown of glycogen to glucose, correct? And glyconeogenesis would be the formation of glucose to glycogen, right? So do you understand the terms? Terms play a big role in these science courses, right? Now this stuff is cell bio, okay? But you need to have an understanding of these three fibers to make this make sense to you, why things work the way they work in our body. Now if you're a couch potato, you'll have more of these, some of these, but hardly any of these. Why? Because your muscles never get put through demand. They have very few mitochondria. Why do we want mitochondria? Right. That's where cellular respiration takes place. In the like mitochondrial disease, these people fatigue out right away. Why? Because they don't have that ability to go into fast oxidative. They can't. So they poop out. Muscles fatigue very quickly because they don't have enough mitochondria producing, your aerobic activity. They stay in an anaerobic phase. So you can't demand the muscle then. So what happens if the couch potato decides to work out? You're going to start running.
They fall, pass out.
They fall and pass out.
No, their muscles would keep time.
The muscles fatigue fast. They don't fall, but they don't have a heart attack. But they don't fall and pass out. They don't have it right. And she's sitting it on the edge because what happens to these people in the cytoplasm is where glycolysis takes place. In the mitochondria is where cellular respiration takes place, so there's oxygen in there. That's where your oxygen levels are high to break this sugar. So the key is this, glycolysis is going to take one glucose molecule, which is a 6-carbon molecule, it's a big molecule, and you're going to give me a net of 2 ATP. That's a joke. Comparison to these guys, they're going to take one glucose molecule and give me anywhere from 30 to 36 ATP, depending on where I am.
That's including my phone, so.
No, it is. I know. I take 2 away, so you're still going to get 28 to 34. But you follow what I'm saying? You're still going to get a lot. So the thing is, it's much more efficient burning of the fuel than the other way. So what happens to these people? Why do they get so much pain? Well, she was hitting it on the head. What happens is when you go from glycolysis, you take a 6-carbon molecule and you put it in 2 3-carbon molecules known as pyruvate. Pyruvate then will enter the Krebs cycle and means I'm the mitochondria. It circles twice to get rid of the carbons. But now I produce more ATP. Then the byproduct of that will enter the electron transport system, which will fire through. And every time it fires an oxygen molecule, a hydrogen atom is given off, and you make an ATP. So that's how you make the most of the ATPs in the electron transport. All this is in your mitochondria. So if I don't have mitochondria to go into, now what happens with that gluconic acid, it converts to lactic acid, which builds up in your muscle and fatigues the muscle quicker. You get the painful nodules in the muscle, and that's what happens to these people. But as you keep training and pushing yourself, muscles will start to develop more mitochondria than you need, and they will. The cells will start to produce more mitochondria. It's going to have, if you take out more oxygen than air. And that's why you can start with running a half a mile, and in 3 months you're running 4 or 5 miles a day now, and you're not pooping out anymore. The muscles aren't cramping up anymore because of that change. So where would we need this? Well, fast glycolytic muscles are designed to react quick, reaction time. Burn your hand, pull your hand away. So mainly upper extremity movement is primarily stays fast glycolytic. Okay? Slow oxidative, these muscles will constantly contract and relax, and they really don't fatigue out easily. These are your postural muscles. So you don't so you don't fall down. Just sitting there, your muscles are working your upper back to keep you erect.
It's the S slow.
That's slow. They don't need to react fast. And primarily your smooth muscle and cardiac muscle are mainly all slow. They don't have to react quick. They just gotta constantly react and not fatigue. And that's the idea of postural muscles. They take a long time to fatigue them out because they fire very slowly and rhythm. So different nerve fibers would hit them. This, the fast oxidative, those would be down into your lower extremity area from running. So that's what they say. If you can use a lot of your quads, your thigh muscles and stuff in your workout routines, you burn a lot of sugar. You burn a lot of calories, other than just using your arms. You burn a lot. So this is why swimming burns so much. You're using everything. You understand? So the more you can, so that's why aerobic exercise, running, fast-paced walking, swimming, bicycling, any of these type of sports, you burn a lot of calories because you burn a lot of sugar. I hear a lot of people talk about, yeah, juices and fruits are good. Yes, they are good for you, but not overabundance of them because that's hidden fat. What do I mean? What does sugar store
It's
as?
not fat. Well, it's carbs, but
But what do carbs store as?
fat.
Triglycerides. They'll raise your triglyceride levels to the roof. You're better off eating protein than you are taking in carbs.
Yeah, we're obsessed with low fat in this culture, and they're coming to see now that.
That's
low fat
wrong.
is
Low fat's
sugar.
wrong. Now, if you're going to have a low fat product, make sure it's a low sugar product too.
Yeah, that's exactly the place.
But that's the lie. They took fat because the essential fatty acids don't cause cholesterol, don't cause anything in you. That's a misnomer. Cholesterol is produced by the body, not the diet. And research has been done on this, and Dr. Toppy was involved when he was first practicing as a doctor in a huge research study done by Harvard Medical School. He was involved with that, okay? Where they took these people, changed their diets, and had them run them for 10 miles a day for a 6-month period. The cholesterol levels then and post. Cholesterol didn't change. It's changed by 2-3 times. Tries will change because that's diet related. But cholesterol did. So the body produces cholesterol. Why? Because we need it for hormone formation, cell membrane formation, for healing. We need it, antibody formation. So cholesterol is an important product. Some people end up producing too much, not enough though, of the heavy density. That's the problem. That's the one that will stay liquid in our system and not stick to something and create, a clot, not a clot, but create a, what I mean, lungs to form. That's the worry of the ratio being low. So when your LDH ratio is like 3 times your HDL and your triglycerides are like way astronomically high, your medical emergency. You're a CVA with that. Cerebrovascular accident. So that's what you look at on a profile. But if I got cholesterol that's 250, which is high in today's standards, but the majority of the molecule, 40% of it is HDL, there's nothing to worry about. I can have cholesterol of 140, but only 10% of it is HDL. That's more to worry about than the person with the high cholesterol. So you got to look at, go into the lipid levels and look down at the lipids. That's not just the total molecule. So they make this total number, 200. When I was going to become a doctor, it was 300. And they haven't really changed that much. So the statins go in and play with the cholesterol. What are they doing? They're making the liver kind of sick so they can't produce cholesterol. That's what's happening. So I remember a case that when I was at a seminar on all this stuff, going back about 4 or 5 years ago, and we got into this. We talked about a patient, and the woman was like 82 years old. And for her whole life, her total cholesterol molecule was 400. But over 45% of it was HDL. Well, the primary decided to put her on statins. She died in 6 months. Because that cholesterol was not going to cause a problem. That was normal for her body. See, there's a lot to consider now. The triglycerides are through the roof. That's diet related. That's diet related. You understand? That's different. That's why you have to fast. Fasting doesn't change your cholesterol that much. Fasting affects sugars, your fasting blood sugars, of course, and your triglycerides. Those two things, those lipid profiles, you have to fast for them to be active. If you don't fast, they're not active.
Do you mean the fasting that is between
Well,
dinner and breakfast?
No.
Okay.
No, we're talking like a 12-hour fast. I'll ask you, have you eaten anything this morning when you got up? You say, eating or drinking anything. Because believe it or not, just drinking water can stimulate the process and throw off the levels. You stimulate digestive enzymes that can turn the liver on and make it do things that you don't want to do yet. Now, if you fast, what do you say? You know what? I'm going to beat you. I'm going to 16 hours. And everything will be low and screw that doctor. I take, well, guess what's going to happen when you fast 16 hours? Your body goes into glycolysis and starts taking sugars out of your liver and breaks the doctor's knees. And what's going to happen? Triglycerides will go off, fasting blood sugars go off. So why do the A1C more important than fasting? That shows you what the sugar molecule looks like in 120 days. So a red blood cell lives 120 days. They can see for 120 days what your blood sugars stay at. You're in the right level. So there you go. So that's why as time goes on, they test differently than when I went to school. So you're always learning. There's no such thing as, oh, I graduated, I don't learn anything else. No, because what you're doing today, 10 years from now, maybe as backwards in English. And it is when it comes to the diagnosing things. They've changed so much. They've made it easier. It was harder 30 years ago to figure out what's wrong with someone than it is today. Years ago, you really had to use your brain to really test the living hell. We didn't have all this nice testing that they do today. One of the best things in the world is the MRI. Okay? So just know what each one is, which each muscle group it would affect. And that's why you get to know about it. Okay? That's about as deep as I'm going to go on you with it. Because the rest of it is physiology, not anatomy. But you do have different muscle fibers within a muscle. You know, and you can see if this was really a nice color, one would be red, pink, the other one pale. Pale means no oxygen. So no oxygen, no what? Myoglobin. What's myoglobin? Protein that holds oxygen. Which is similar to hemoglobin. That's in your muscle, myoglobin. Okay? And then this is showing you long muscle tissue versus someone with muscular dystrophy, which is pretty nasty. You get this fatty infiltrate. So as muscle tissue dies, it gets replaced with fat. So the child may look normal, but bigger than a normal kid. Wow, how rugged he is. See that child when he's about 8, 9 years old versus one that's 3 years old. So in that, you would have hormone levels through the roof and all this other stuff. And what's the danger when muscle breaks down? It releases proteins. And what's bad about too much protein? It's going to do to the kidneys. It's shut them down. It's going to shut them down. It's going to cause kidney failure. And that's usually in the end of what takes you. You go with the kidney renal failure. The kidney can't handle all that protein. That's what's bad about overprotein in your body. Other than causing a lot of reflux in your gut, as it does. It's an amino acid. And think about what it's doing to your kidneys. So a lot of this, you know, now if you're using the protein drink as a meal supplement, that's fine, because you're not eating right, so you're taking and stuff like that. But you know, the best way to take anything in your body is in its own natural form. Meaning not in a pill form, not crushing it and grinding the hell out of it. Eat it. Now, if you can't do that, then do the other stuff. That's fine. But still, you go back 100 years ago, people who lived differently, seemed healthier, and they kind of were because they lived out of the earth. They were taking all the minerals from the earth into their body. Because if you break our bodies down, we're made of the same stuff that's in the ground. You take a general bio, they go into that. Into the actual chemical makeup of us and the chemical makeup of the ocean. And physiology does a good job of showing you that when you get into some of the chapters. Where we derive from. So it's pretty cool. Okay? So that's that part of muscle. So now we're going to start going towards. One thing here is, I think it goes into detail with the cardiac. Not the look, but how it runs. Showing the nervous system, but notice the key things here. Mainly aerobic. I mean, smooth muscle it doesn't really perform well now. Only aerobic. This is why, you know, when you close off coronary artery, we have major problems. Like, Houston, we have a problem. Because now we have no oxygen going to this. And when we get to the house, we'll learn about the widow artery and all this stuff. That, you know, let your husband keep giving him the fried, greasy food and stuff. You know, when I was going through school, olive oil and avocado were the worst two things you could ingest. 100+ you're going to die. Where today we realize, no, the type of fats that are in there, your body can handle and keeps them liquefied and it doesn't store them, no end. So it's amazing how, you know, now they're back with coffee's good for you, then coffee's bad for you. You know, one thing you never see that's good for you is cigarette smoke. It'll never be good for you. So if there's one habit, there's no such thing as moderation of it all hurt me, is cigarette smoke. That's both. Okay? But if, you know, they're on the marijuana issue now, alcohol will not be approved today because of the damage it does to the body. Because nobody just has this much wine and that's it. You know, when the bottle's gone, then you're done. Ooh. So,
It's cancer.
huh?
It's cancer using red wine. Coming out with studies about that right now.
But I don't buy it. I've always learned one thing, no. I'm going to teach you something scientific. Never go with the new data over data for 50 years.
No, I
You follow what I'm saying? That could be one study and this and that, but in general, red wine is probably one of those healthiest things you can put in your body, especially for the heart and cholesterol. Cardiologists will encourage you to drink a glass of red wine a day.
just not a glass.
Well, an ounce, you know what I'm saying? It's only a glass doesn't mean like a gallon. They're talking this. You know what I'm saying? Because a lot of studies were done on the natural side of controlling fats and cholesterol, using choline and acetol, vitamin E, and all these other ingredients, B vitamins, and they do work. The missing ingredient though, to lower the ones on the fats to get rid of it. It's alcohol. That it puts your body temperature to rid. So alcohol will put it in a liquid form and get rid of it. I'm not saying drink a bottle of scotch a day. No, that's not what I'm recommending to you, not at all. But the point is, you know, is it going to cause severe harm to you to have moderation in one or two glasses a week? No. Thing is, people lose control, they can't do that. You're stressed. You pop a Valium when you feel even better. It's like, it's the best thing in the world. But it's not. You're killing yourself. Okay, so just remember that. So the only thing in moderation that's totally not good is cigarette smoke. No. But you gotta remember, the marijuana has less side effect on it, you know. And the state want to get rid of its deficit, legalize.
Oh, yeah, that's
The
like.
deficit would
rural
be
here,
gone.
everybody-
But don't let individual vendors sell it. The state owns it, the state sells it, and takes the money from it, like New Hampshire does with alcohol. They sell it, they own it. That's why there's no deficits in New Hampshire like Rhode Island, because they do it the right way. So you can't let the little kooky people run it. That's the problem.
You can't tax the hell out of it, which they're gonna do anyway. That's what
Yeah, they
they're
will.
gonna run
They
It
will.
looks
Like
like
they
it
don't
was
say,
citizens back
look
when.
at the tax on smoking. When people stop smoking, no.
Yeah, exactly, so it's
Yes.
not gonna affect it, so they might as well.
Well, you
Tax
did,
it
but
out.
in general, people are still smoking.
It's costing me like $20 a day.
Well, you got money. Oh, that's even more. No? You don't smoke, or you just pump this thing.
How much is it?
$12.
$4.
A lot cheaper.
It's on a really nice day, you can more about today than on the ones. I don't know about that. Okay, you say that.
Well, everybody's got reasons why they do stuff, so you can't. You know, it's easy for someone that doesn't have a bad, we all have bad habits, so, all of us. Kirk, me too.
No, I actually stopped because I saw my daughter. It was mainly using chew.
Oh, true, that's,
Yeah.
no, I don't mean that, I mean cursing, like, Steve, that's the way I mean that.
But I stopped because my daughter spit into an empty bottle. And I looked at her and I'm like, what are you doing?
Oh,
I'm
true,
like,
that.
Daddy.
That's right. You don't like that? See, well, you're not. But, okay, so now we're gonna get into, we're in the next chapter now, muscle, how we make a muscle. We're just gonna cover this, and then we're gonna get into movement and stuff with you today, we'll do that on Friday. But, how we get put muscle names. Well, muscles are kind of named by how they're shaped, what they do, what they attach to, or what it relates to. So the muscles get named any way you want. But there's a generalization of how some of them classified. Parallel muscle means the fusiform in the strap. This is an example of a parallel strap. S-T-R-A-P, a strap muscle, because it's long and thin. It's crossing two joints. That's what we mean by the term parallel. So it's crossing two joints. Its shape is strap shape. It's thin, long. The prime example is sartorius. What do I mean? It's crossing your hip, it's crossing your knee. Its origin would be the ASIS. Its insertion is the medial pes anserine of the tibia. That's where it inserts. Pes anserine is 3 muscles insert. That's into the medial condyle of the tibia. That's where this thing is going to insert. Its job is to cross your leg. This movement here. We'll go into the movements after. But that's why you can cross your legs. Thank you, sartorius. See? Thank you, sartorius.
It's the one to uncross.
The uncrossing the outside muscles. Nice. Well, that's to cross the leg this way. The adductor is take that line, put it back in the classroom, get it out of that. Okay, but that would be, there's your example. Parallel strap, sartorius. Just memorize the damn example. Nothing else to worry about if you do that. Then we go into the fusiform. Well, this is a parallel too, because it's crossing two joints, the shoulder and the elbow. And what's an example? Biceps brachii, the typical Popeye muscle. The big round belly with the 2 tendons coming off each side. Popeye eats the spinach, he gets a nice big biceps, and usually there's a tank in there shooting a gun, whatever. I was a kid, it was a big cartoon. Popeye.
It crosses the shoulder and what?
Elbow. If it didn't cross the elbow, how would it flex the forearm? Think of its motion. That's why you have to learn generalized origin and insertions of these muscles and understand their action, or you just memorize it. If you understand action in compartments, there's no memory. You've got to figure out where it is and what it's doing. And that makes the practical, the next lab exam, so easy to ace. Where you really couldn't categorize bones that way. The bone marks. The bone marks are just, in plain English, a bitch, and you're going to put the terms in your head. Look at your hands about it. But the muscles, no. And before we finish up the muscle chapters, I categorize them all for you and where they are. Because we're going to test on them once, and then we test on them again, and we bring nerve in, and nerve innervation all. So that's why we damage your nerve when you just can't move, and that we'll learn all that. So we start making it a lot more interesting once we get out of this dry stuff. Poof. Okay, that's like, oh, this is nice. So the next muscle type to go to, so those were your parallel. Not pennant. It's not baseball season yet. Don't know the pennant. Pennant. So we have the first type, a uni pennant. Uni means one pennant. And what do they mean by that? We only have muscle fiber on one side of this tendinous insertion that travels through it. This tendinous insertion that travels through it, I only got muscle on one side. It's like getting a feather, cut the feather in half, just got feathers on one side, and on the other side, that grain, that vein running through it is nothing. That's what this muscle looks like. Prime example is extensor digitorum longus, which is in the anterior leg. What do you think this muscle does when it contracts? Would you say extends the toes? The answer to that is yes. Why try this? Listen to its name. Extensor digitorum digits. Longus means it's a long muscle. If it was a short muscle, it would be called extensor digitorum brevis. So longus means long, brevis means short. So that's how you term muscles, long or short. Longus, long, brevis, B-R-E-V-I-S, is short. So if a muscle would be termed extensor digitorum brevis, then we know it's not long. It's not just about crossing a joint. But this thing is long. It's all the way up in the air. It sits right next to the tibialis anterior, which you're going to learn in lab next week. how do you feel your muscles? Well, you can. A lot of fun. Just move it along if you want to watch it. But if you just put your hand here first and bring your whole foot back, I feel, well, this is the tibialis anterior.
Okay.
Now, I move over a little lateral, then I look at my toes, and I feel this muscle tightening under my, there you go. That's how you do it, figure out where they are.
Is that for balance as well as like on your toes?
It would aid and help you, it's not gonna stand you on your toes, because the gastrocs and soleus would stand you on your toes. But yeah, it would balance when you got, you keep the toes under control, that they don't over, you know what I mean, that they don't flex themselves, they stay in that mode of where they're holding out, extended, and away from one another, abducted. So it would help. To keep good balance, everyone's gonna be working on this. Believe it or not, just cut your little toe off, your whole balance changes. And we'll show you that with David, we'll cut his toe off. We'll show you. I got a lot of this girl. Okay, so that's that one. So we got a unite pennant. Of course, we're going to have a bipennant. Bi meaning two. So you got muscle fibers on both sides of the tendon insertion running right through the center of this muscle. And guess what this one's name is? Rectus femoris.
Keeps your feet up.
Put your femur up. It also extends your knee, right? So rectus femoris is part of your quadriceps. That's the most commonly pulled muscle when you pull your quads. It's usually a tear right here. Where the muscle fibers and the tendon insertion meets, the tears right in this midpoint. And it hurts like hell. It's common like when you play a real heavy contact sport, especially if you're a lineman, and you're pushing someone out, and you're pushing heavy with your thighs, and the person just drops. What happens? The leg goes from a flex to an extension, quick, tears the muscle. And this thing will plague you now for months to heal. So, or carrying heavy, like you did in the military, climbing up the side of a mountain, and climbing through. The legs, almost your leg slips off, and it's like, oh, damn, I can't move it now. There you go. You take a muscle and heavy contracted flex state, and let it drop into a quick extended state on it. That's how you do it. If the fibers don't only go fast enough, they tear. And that's what she likes, is muscle tears. She tears muscles and just stay away from it. No, I'm just teasing her. But I see like a lot of research stuff. They always seem to be reading, which is really good. We'll go far in the field wherever you go into, but you like doing that. So rectus muscles in general normally have tendon insertion. And what's the one that's the six-pack? There you go, rectus abdominis. It has 3 tendon insertions within itself, hence looks like a six-pack. That's why it's the name six-pack. The rectus abdominis. Unfortunately, it's a very hard muscle to see in most people. It's in everybody, but it's hidden. We all keep it hidden. We don't want you to see it. It's hidden. So you need it somewhere between a six-pack and a keg. Somewhere in the middle. The keg is very expensive to maintain compared to the six-pack. You got to put a lot in there to keep it going. So this the rectus muscles usually have a lot of, have tendons and insertions in themselves. The last of the pennants, so if you're 3 or more, you call them multi-pennant. And the prime example is your deltoid. Deltoid is many muscle groups coming together with tendons and insertions within themselves. Hence called a multi-pennant.
You say that again?
It's many tendons and insertions within 3 muscle groups. Hence called multi-pennant. You can see them. You're not seeing it on the back side, but each one of these muscles would have multiple tendon insertions through themselves. So your deltoid is the prime example. There's others, but we'll just hit you with the prime example. Okay, that's where we're going to go for testing. Now, we have also the difference between the multi-pennant is a convergent muscle. Now, a convergent muscle means we have this huge origin and convergent to one narrow insertion. Converge to one narrow insertion. That's why it's called a convergent. The pec major is perfect because look how big, this is all origin. part of the muscle is origin. There's a little insertion point on the anterior lateral aspect of the humerus. And there's nothing funny. That's that lateral ridge that goes on the humerus. That's what that was. Because you're going to learn there's a lady between two majors. And the latissimus dorsi will insert between the pec major and the teres major. Hence, the lady stands between two majors. You were once a major. So notice it, a broad line. So what would be its origin if this was, think of a chest, this would be clavicle, all of the sternum, down to the costal cartilage and ribs. So what a huge origin this thing has. Insertion point, anterolateral aspect of the humerus. Its job is to do this. Feel your muscle, pull your arm in. So that, adduct the arm across your chest. That's that. What's going to initiate the movement with it? Minor. And coracobrachialis. You got to think of the muscles. Coracobrachialis. So those are going to contract to stop. The pec major can take it over now because of the way it's built. You can pull it all the way in. But other muscles will help. Understand? Other muscles will help. And the last of the muscle groups I'm going to be in for today is, last but not least, our circle muscles. You have orbicularis orbis, orbicularis oculi, orbicularis ani. Where would that be? That's your front. That's where your eye is down there, your third eye. But what do they do? It's kind of like designed to close off an opening. So it's almost describing a what? A sphincter. But it's a sphincter made of skeletal muscle, not smooth muscle that you're so used to studying. Because we have tons of sphincters around hollow organs, right? Stomach, bladder, uterus. You're gonna close this thing off. So this is your learned response of go from diapers to the toilet. So this is where you train these muscles to work, that they just don't stay open all night and everything comes out. I mean, eventually you will go back to that phase, but you start in diapers, you end in the pens. It's true. Unless you're lucky enough to die before. Not awful, but that's what we get to look forward to as we get older. So, next class we'll start getting into muscle groups and names and where they are and stuff like that. So you have a quiz next, you got a quiz on Friday.